thank you very much for listening to this talk. This is an application of probabilistic numerics to partial differential equations. This is going to be a relatively short talk about joint work that was done in collaboration with John Cockayne, who's now a postdoc at the Alan Turing Institute, Robert Aykroyd, who's at the University of Leeds in the stats group there, and Mark Girolami, who's in the engineering department at Cambridge University. So, as I said, this is an application, and it's an application in data-centric engineering. So the motivation here is to properly monitor and control one of these pieces of industrial equipment. So this is called a hydrocyclone. And the purpose of a hydrocyclone is to take a liquid that is sort of contaminated in some way with solid particles, or perhaps contaminated with some liquid of a different kind, and to separate the liquid into essentially water plus whatever else was in the liquid. So these are used very widely in industrial settings, and this is basically how it works. So you take your contaminated water and you shoot it at a high pressure into this chamber here, and this chamber is conical. So what happens is you get a vortex formed in the chamber, and the centrifugal force basically pushes the heavy particles out towards the boundary of the chamber, and the lighter particles and typically water are therefore in the middle. So if you have a tap in the middle of the chamber and you open the tap, you get sort of purified liquid, typically water. And if you have a nozzle at the bottom, you open the nozzle, you get the heavy particles due to the way that the chamber is shaped like a cone. So this is how a hydrocyclone works. And for it to be effective, it has to operate at high pressure. You need the high velocity to create the high centrifugal force to do the separation very cleanly. So that in itself means that there's a sort of a need to monitor these things closely and to ensure that they're operated safely. So if you don't have the proper separation of the liquid from the contaminant, then it could be the case that if you open up your liquid overflow here, you end up getting contaminant out, and that can block whatever process follows on from here. So it's very important to monitor these things carefully to know when it's appropriate to open the taps and when the pressure should be lowered or raised in order to get the optimal separation of the liquid from the contaminant. So one of the ways that's been proposed to tackle this problem is using a non-intrusive imaging technique called electrical impedance tomography. So the reason for this is that when you look at one of these hydrocyclones, you can't directly see inside one of the chambers. So you don't know whether there's this good separation until you open the tap. Electrical impedance tomography is a way of trying to infer what's happening in the chamber without directly opening it. So EIT, as I'll call it from now on, was really motivated by medical problems in the first instance. So it's a non-invasive imaging technique. The idea is basically that you take the body that you want to image, so this might be a patient, and you apply electrodes around the outside of the patient. So this is a diagram that John drew for this talk. You apply current to a subset of the electrodes. So typically you take a pair of the electrodes and you apply a current through them. And then you measure the voltage at each of the other electrodes. And the voltage that you measure will have resulted in a sort of indirect way from the fact that the current has to pass through the conductive or semiconductive material in the patient. So it turns out that different tissues and different organs have different conductivities. And the voltage that you see at one of these electrodes tells you some information about the conductivity of the tissue that the current has passed through. So if you had a physical model for how current passes through tissue of different conductivities, you might be able to reverse engineer the conductivity of the interior of the patient here, and by proxy say something about where the organs are, for example. So this is the idea of electroimpedance tomography, and that physical model looks like a partial differential equation. So this partial differential equation, or PDE, describes how the voltage, V, or the green terms here, are related to the currents that are applied, the I's, or the blue terms here, as a function of the interior conductivity of the patient, or of the body being imaged, and that's sigma here. So conductivity is a field, and it's indexed by x, which is a spatial coordinate. So if x was a location in the lungs, maybe that has a different conductivity to if x was a location in the skin, or something like this. The electrodes are a subset of the domain, of the boundary of the domain, and they're denoted E here. And this set of equations here is called the complete electrode model. What it means, the meaning of complete here is that you're modeling the electrodes as sort of continuous strips along the boundary, and there's certain terms that are explicitly capturing the fact that electrodes are typically not completely perfect. So this is quite a physically realistic PDE. Now, not at the moment, but later on we're going to talk about the numerical solution of this PDE, and it will be worth just remembering that this is a second order linear PDE in terms of the solution V. Okay, it's non-linear in terms of the conductivity field, but it's linear in terms of its solution V. This is just a technical aside, but for the experiments that we actually run a slightly simplified version of the physical model, which models the electrodes as point electrodes. Okay, so from a statistical point of view, we need to estimate the conductivity field in the domain that we're imaging on the basis of a finite number of current stimulation patterns and voltages that we measure. And that's a statistical problem or an inverse problem, depending on what you like to call these things. It's also an ill-posed inverse problem, because this conductivity field is essentially a two-dimensional or perhaps three-dimensional scalar field. So it's a function of the spatial location, and in principle that could be infinite dimensional. However, the amount of data that we're able to measure and store is finite dimensional. So in terms of just a mapping from data to conductivity fields, this is not a well-posed problem. So we obviously need to impose some statistical regularity. And in this talk, we follow the Bayesian paradigm for performing inference. So Bayesian inference for the complete electrode model was studied in some detail by Matt Dunlop and Andrew Stewart in their 2016 paper. But for anyone who's even remotely familiar with Bayesian statistics, the idea is clear. So you place a prior on the unknown conductivity field. So we just call that pi sigma. And then we obtain a posterior by combining the prior with the likelihood through Bayes' theorem. And I've written Bayes' theorem in this way just because when we have infinite dimensional objects, we can't work with densities. We have to work with Radon-Nikodym derivatives, but this is just a technical aside. And this is the likelihood, up to some constant of proportionality, which doesn't matter. So this will depend on the unknown conductivity field and depend on the voltages and currents that we measured. Okay, so we need to specify exactly what the measurement error model is, what this potential phi is, and we just went with a squared error measurement model with a known measurement noise. Now that's not particularly motivated by the experimental equipment because we're not experts on that, but for the purposes of this talk, we'll just assume that this model is suitable. Okay, so here's a picture. On the left, you see one of the canonical test problems for electroimpedance tomography. So this is a dish that's got these sort of gels in, and they're supposed to represent organs, but it's just a crude toy problem. Around the outside, you can see that there's electrodes that have been strapped to this. What we've done is we've taken the current and voltage data obtained from this experimental setup. We've instantiated a Bayesian inferential framework for the conductivity field. We've used a high fidelity PDE solver to solve the PDE, and we've run a Markov chain Monte Carlo method to sample from the posterior distribution. Now, I'm obviously glossing over details like how the prior is chosen and so on, but let's assume that that was fine. We get a posterior distribution for the conductivity field. And we can summarize that in various ways. It's a complicated object, but here is the mean, for example. So this is the mean for the conductivity field sigma computed by averaging over the MCMC output. And what you can see is that the conductivity field looks like a meaningful proxy for what's actually in this domain here. So the gel here has a different conductivity from the surrounding fluid, and that is manifest in the inferred conductivity field. Okay, so that's great. And this medical imaging technology could potentially be very, very useful without any additional work. But the problems that are raised by the hydrocyclone are really about the time scales involved. So this fluid is spinning around at very high pressure, and therefore it spins very quickly. And that doesn't necessarily lend itself very well to this kind of inferential pipeline where we need to run MCMC for many iterations to get a nice average. We need to do things a bit more efficiently. And this MCMC is gated by having to solve the partial differential equation at every single time step. So what we're going to do now is we're going to formulate EIT for the hydrocyclone. So that means we're going to introduce the time dimension, and then we're going to talk about how we can overcome this bottleneck that's formed by solving the PDE repeatedly. So in the context of the hydrocyclone, the conductivity field is a function of both space and time. So we're going to carry on operating in the Bayesian framework, which means that we need to put a prior on this conductivity field. And there are many ways to do this, but I think probably the most accessible or intuitive way is to explicitly write the conductivity field as a linear combination of certain basis functions. So we're going to do something that looks like this. So these phi i's are spatial basis functions. They depend on space but not time. And these psi i's are temporal coefficients, temporally evolving coefficients that depend on time but not space. So these phi's are going to just be some fixed basis, but these psi's are considered random in the sense that the epistemic uncertainty that they represent is our prior uncertainty. And for convenience, we're going to take these psi's, these coefficients of the spatial basis functions, to be independent Brownian motions. Okay, so what that means is if we use the notation sigma k for the conductivity fields at time k, then these increments, the change in the conductivity field between two consecutive time points, is a spatial random field, and it's distributed as a Gaussian random field with this, well, I haven't defined this, but with a particular covariance structure. Okay, so if we think about what it means to perform inference for the conductivity field of a hydrocyclone, it's essentially a filtering problem. So we have a conductivity field at each time point such that the evolution of the conductivity field is a priori modeled as a Markov and Gaussian process. And we have observations at each time point of the conductivity field which occur indirectly through the partial differential equation model. So we observe currents and voltages at each discrete time, and they are indirectly and non-linearly related to the conductivity field. So we need to perform filtering. We need to estimate the conductivity field on the basis of these measured voltages. And this is intractable in real time because of the PDE model that must be solved to relate the voltages to the conductivity fields. So that's where probabilistic numerics comes in. So the general idea of probabilistic numerics is that you can represent uncertainty due to discretization as a probabilistic object. So the paradigm is very similar to Bayesian statistics. So in Bayesian statistics, anything that you don't know is considered random, and it has the same sort of philosophical status as a random variable might in a generative model. You just take all of your randomness and combine it into a joint model and perform the conditioning and marginalization as required. And the same is true in probabilistic numerics. If you're trying to solve a PDE, Well, you treat the solution as a random variable, and you integrate the uncertainty associated with the solution into your sort of scientific conclusions by marginalizing over that uncertainty to get a distribution over parameters of interest. So that's the idea. I'll show you that in more concrete terms now. So each time we want to evaluate the likelihood, we require the solution of PD, and we're going to try and use probabilistic numerics to avoid that high computational cost. There's lots of, well, I say lots, there are some choices for probabilistic solution methods for PDEs. And the one that I'm going to use is one that John developed during his PhD thesis, and it's called a probabilistic meshless method. It's essentially a Bayesian analog of a classical meshless method from numerical analysis. So the way that this looks like, we start with a Gaussian prior on the unknown solution of the PDE. So remember, the solution of the PDE is this thing called V. And I'm not going to talk about prior elicitation, although it's interesting and important, just because I don't have time in this talk. So what we would like to do is to consider strong solutions of this PDE that satisfy the governing equations at a discrete number of locations. So the PDE is the following object here. It consists of a differential operator A, which is this sort of weighted Laplacian type differential operator, and this boundary operator B. Now, in order for V to be a strong solution of the PDE, it must satisfy these equations at all of the x's in the domain and all the x's on the boundary. What we're going to do is we're going to condition the random variable V that was introduced up here on satisfying these equations at a discrete and finite number of locations. So it won't be an exact solution, it will be an approximate solution, but it will have associated uncertainty. So how do we pick the locations? Well, you could formulate this as a problem of optimal experimental design, but for the sake of doing something convenient, we're going to introduce these blue crosses, which represent the locations at which we're going to ensure that this part of the PDE is satisfied. And we're going to introduce these orange circles where we impose the boundary conditions, this second condition here. So by refining the grid here, by introducing more blue crosses and orange circles, we will be conditioning on more equations holding, which will hopefully reduce our uncertainty with respect to the actual solution of the PDE. So that is the plan. How does this actually happen? Well, it exploits the well-known conjugacy of Gaussian distributions under linear transformations. So actually, if I return again, sorry for the jumping between slides, to this slide here, the differential operator A and the boundary operator B are both linear operators. And so when we condition on the differential part and the boundary part being satisfied at a discrete number of locations, that's just conditioning on linear functionals of the GP. And it's well known that this can be done in closed form. Now, the equations are a little bit nasty, and I won't go into any detail here, but the take-home message is that this is completely straightforward. And what we get out is a posterior distribution over the unknown solution of the differential equation. It's a mean function and a covariance function that we can compute. I mentioned that this probabilistic meshless method that John developed was a probabilistic analog of a classical meshless method, and what I meant was this posterior mean function is actually exactly a classical meshless method for solving PDEs. So this thing is recognized as a classical object, but what we've done is endow it with this probabilistic structure that in the Gaussian case is just represented by having this covariance function as well. Okay, so as I said, in the Bayesian paradigm, you just form the joint distribution of everything that you don't know and condition and marginalize a way to get the quantities that you want. So what we do is we say, well, we have the measurement error likelihood, and we now have additional uncertainty due to the fact that we don't know the solution of the PDE exactly. So that means that V, this solution of the PDE, is now a latent variable that needs to be marginalized. How do we do the marginalization? Well, we take our posterior from the probabilistic meshless method, and we integrate the measurement error likelihood in order to remove or marginalize the unknown solution of the PDE. Now you see why we chose a Gaussian measurement error model. It actually means that we can do this marginalization in closed form. And what happens is the posterior distribution for the there's a closed form expression for this marginal likelihood, which is a Gaussian. And what it looks like is this part here, which is the measurement error model, but the covariance is inflated by a matrix here, which is the posterior covariance matrix for the PDE. So what's happened is we've acknowledged that we haven't solved the PDE exactly. There's uncertainty with respect to that latent random variable. And we've marginalized over that uncertainty in order to inflate the Gaussian covariance here in the measurement error model. And what that implies is that the posterior is going to be less informative in order to account for the fact that we've got less confidence with respect to the solution of the PDE. So I hope that's clear. I'll show you this in action in a minute, which will hopefully clarify what's happening. But what in principle it allows us to do is to pick a budget with which we're happy to perform computation related to solving the PDE, and then to perform inference in a way that is adapted to that computational budget and acknowledges discretization uncertainty due to working at that computational budget. Now, this is all going to be used in the context of an inverse problem for a conductivity field, and therefore some auxiliary computational method is going to be needed to sample from the posterior for the conductivity field. Now, that wasn't really something that we focused on in detail. So the results that I'm going to present are based on a sequential Monte Carlo method. Now, there's no particular need to do that. We just found that it worked well. And in fact, this would probably not be practical in the real-time filtering context of the hydrocyclone. That's going to be further work to bring this up to real time. But we just wanted to have something that worked for the purposes of exploring how the probabilistic meshless method interacted with the inverse problem for the hydrocyclone. So sequential Monte Carlo, I won't go into any details, but it's essentially a way of approximating the posterior for the conductivity field in a principal way. Right, so let's have some results. So we actually worked with an experiment that Robert and his colleagues in Leeds performed in the lab. So this is a beaker that they filled with water, and they strapped electrodes around the outside. And then what they did is they stirred this beaker with a pen, so very scientific, and after a certain amount of time, they used a syringe to add a small droplet of salt water. Now, salt water has a different conductivity to regular water, and that should show up in the inferred conductivity field. So the question is, can we recover this salt water as it sort of spins around and diffuses in the beaker? So this is really a toy model for the hydrocyclone that's at pressures low enough that it's safe to use in the lab. So here's what happens if you don't worry about discretizing the PDE and you spend huge amounts of computation to get a very accurate solution of PDE, and then you run NCMC for a very long time, and you compute your posterior means at different time points during the experiment. This is what you get. So the salt water, the saline, saline fluid was injected at time 10 in the time index of the experiment. So just afterwards, we see that the conductivity here is different to the conductivity elsewhere, and that represents where the saline solution has been added. I think it's probably still being added at this point because at the next time step, it's more clearly visible. And then what you see is that the salt water is sort of spinning around here as we move through time. It's getting dispersed by the rotational motion of the water. So I guess the water is rotating anti-clockwise as we look at it here. So this is what we would like to be able to do with a limited computational budget so that it can be running real time or close to real time on a hydrocyclone. What we're going to do is we're going to use a cheaper, quicker solution of the PDE and then account for the fact that we've got uncertainty now with respect to the solution of PDE, and that should allow us to accelerate all the computation that we need. So here's how this looks. So we're going to consider a sequence of different discretization resolutions here. And I'll quantify the resolution by the sum of the number of blue crosses and orange circles. And as we increase the resolution, we end up with something that looks like what we would get if we very accurately solved the PDE. So this is the posterior mean, this is the posterior standard deviation. And when we use 523 grid points, we get something that looks very close to that. But when we use fewer grid points, so when we use something like this, we end up with something that looks like this. So this is a posterior mean, which doesn't look particularly close to the real posterior mean if we could exactly solve the PDE. But it's kind of similar in spirit, perhaps. But the posterior variance has been inflated to appropriately acknowledge that this posterior mean, it's not an informative point estimate in this context. So we've got a principal way of trading off the complexity of the PDE solver with the inferences that we make about the conductivity field. And what we can do is we can decide what a computational budget is. Perhaps it's 316, and then we can get this inference for the conductivity field, but we know the extent to which we're confident about this inference. So that seems to mitigate overconfidence compared to the naive approach, where you just use a classical meshless method with a sort of relatively small amount of mesh points and don't account for the discretization uncertainty. So what we're comparing here are these are the temporal coefficients in the prior series expansion at a fixed time, and these are what we are inferring. The gray contours that you see are the exact posterior distributions for these coefficients if we could exactly solve the PDE. The blue contours are the posterior for the coefficients if we just plugged in a classical meshless method into the likelihood model for the data and didn't acknowledge the discretization error. So that's kind of the standard thing to do in UQ at the moment. And the orange contours are what we would get if we used the probabilistic meshless method to integrate out the uncertainty with respect to the unknown solution of the PDE. And what you see is basically the orange contours tend to kind of cover the gray contours. So we've widened the posterior in a way that means that although it might not be centered in the right place, the mass is spread out in such a way that it does cover the same kind of region where the exact posterior ought to be supported. Now, if you look at what happens with the blue contours, that's not the case. So if you just plug in a classical meshless method as your PDE solver and hope for the best, you introduce a bias and you don't appropriately inflate the uncertainty to quantify the discretization uncertainty that should be there. Okay, I hope that was clear enough. So the summary of the contribution is that probabilistic numerical methods can be used to instantiate a principal trade-off between the computational budget that you have and the precision of the inference that you're hoping to make about the conductivity field in the context of one of these EIT PDEs. Now, EIT is not special. There'll be lots of PDEs that have this kind of structure, and it might make sense to use probabilistic methods in those contexts. But this is early work, and we realize that there are still some technical issues to be surmounted. So some of them are the choice of the prior. So each time we solve the PDE, we solve it for a different conductivity field, and it's likely that similar conductivity fields lead to similar solutions of PDEs. So one might expect the prior to couple together the conductivity field and the solution of the PDE in some joint model. Now, how to do that naturally seems quite difficult. Well, let me say that again. There's a natural way to do that, but it's not particularly practical. So there's still methodological challenges involved in setting up appropriate priors that are practically feasible in the context of a PDE inverse problem. The other open challenge is really how to make the posterior computation possible in real time. So we can reduce the amount of time we have to spend on solving the PDE to an almost negligible amount, but we still are burdened with having to run a sequential Monte Carlo algorithm here. So in a sense, this isn't our problem. This is a problem for people that speed up Bayesian computations, and maybe people that use variational Bayesian methods, for example, but it still needs to be addressed, and that's open work. So if you found this interesting, I'd like to just point out where you can find full details. So this is in a paper that was published last year, and it's also on the archive if you don't have access to the journal. Right. Thank you very much.